In this module, Module 6, we'll be covering the various phases involved in doing an exoplanet observation. The 4 phases that we will be discussing include the preparation phase, where, for example, certain pieces of information are collected that will be important later for either the image capture phase or the exoplanet modeling phase. We'll be discussing the phase where the images are actually captured during the predicted transit of the light from the host star. We'll be also covering the phase where various calibration files such as flats, biases, and darks are created. And finally, we'll discuss the phase where post-processing is done of the images, including differential photometry, as well as the exoplanet transit modeling itself. One of the things that will be extremely helpful in all of the phases is if you as the observer prepare a worksheet of the planned observation. Such a worksheet can be obtained on the website astrodentist.com. Some of the items in the worksheet you will see are also automatically filled in. But we ask that if now you could go to the website, download such a worksheet so that you start becoming familiar with the items in it. So let's cover now each of the phases. In the preparation phase, the first thing, of course, is to select the exoplanet target we're interested in covering. And if you recall from the previous modules, there are online resources to be able to predict what exoplanet targets are observable from your location at certain times. Next, as we just said, it's important to collect certain preliminary information on the worksheet. Next, because of those of you who have a German equatorial mount, it's more than likely there will be a meridian flip that will take place during the transit. So it's important to understand and predict when that might take place. So you would be available to make sure that that goes rather smoothly. Selecting the exposure times is rather important because for one thing, we don't want the host star and comparison stars to reach saturation. So in order to select the exposure times, one would first take some test exposures of the target prior to the actual observation time taking place, and then apply some thought as to whether that exposure time is going to result in saturation if, for example, the star is rising, or if in fact the exposure time needs to actually increase because as the star is falling, the brightness of the star will actually be decreasing. So there's a balance between selecting exposure time so the star is not saturated, especially with consideration for it rising, but also to have a large enough exposure time so that there's a reasonable signal-to-noise ratio obtained. Next, we would suggest setting up a number of directories, some of which you see here, one being an analysis subdirectory where files, as we get into the exoplanet modeling, could be stored, subdirectories for the calibration files, the biases, the darks, the flats, and finally a subdirectory for the actual images taking place, which we will refer to as science images. As with any imaging using a CCD camera, it's important to have the CCD camera acclimate itself to the temperature that the observation will be taking place in, and in particular to actually cool the CCD camera to as low a temperature as possible. This would help reduce any dark current issues. Generating flats is an important step in and of itself. You'll see in a bit the importance of generating uniform flats. If you are going to be creating flats using an approach where these flats are created during twilight, let's say, then it's important that they be done immediately before the observation takes place. If you recall, we said how important auto-guiding is, and so it's therefore necessary to make sure that your auto-guiding system is set up and working and is properly calibrated. And finally, as we also mentioned earlier, the importance of making sure that your image capture computer is synchronized to an atomic clock. In this case, we're suggesting the U.S. Naval Observatory's atomic clock. And as you recall, we suggested a good piece of software to do that is the Dimension 4 software. So the next phase after all the preparations have taken place is to do the actual image capturing. The suggested observation time for an exoplanet observing session is at least 30 minutes before the predicted ingress time and up to at least 30 minutes after the predicted egress time. This is so that an adequate out-of-transit baseline can be obtained in order to more accurately model the in-transit drop in light. Now, this could mean, of course, that the total observation session could be several hours in length. As we said earlier, for German equatorial mounts, a meridian flip may have to take place during the observing session. It is important, therefore, that after a meridian flip, image capturing starts up again as expeditiously as possible so that as few data points as possible are lost. This means that after the flip of the mount takes place, it is important to get back on the target star as quickly as possible. Now, this can be done in a number of ways. One quick and accurate way is to use a plate solving method that might be a feature of the observer's navigation software. However, it is also important to realize that in the case of traditional off-axis guiding, and with the camera and the image train not rotated, that the original guide star will no longer be in the field of view of the guide camera. So it's important that when auto-guiding starts up again, that there is a good guide star in the field of view. It should be noted that one of the advantages of an on-axis guiding approach is that the same guide star used before the flip will be able to be used after the flip. So after the science images have been captured, we are ready now to begin the calibration phase. Now in the calibration phase, this should take place immediately after the image capture phase. So this would mean taking our bias files, which are 0-second dark exposures. Typically, we'd suggest an odd number, with dark files taking them at the same exposure time as the science images. So if, for example, the science images were, let's say, 30-second exposures, then the dark files should also be each taken at 30-second exposure. Flats are important, and we're going to cover them in a little bit, but as you're probably aware, there's several methods for taking flat files. These range from twilight flats, where the flats are taken right at twilight time, dome flats if one has an observatory, and a preferred approach, which is a little bit more expensive, is actually having an electroluminescence panel, which is placed on top of the telescope that has very controlled and uniform brightness. The advantage of the EL, or electroluminescence panel, is that the flats can be taken right after the observing session, even in the dark. So one does not have to do the tricky process of getting twilight flats. And the exposure time for the flats should be set such that the average ADU count is around 50% of the linearity of the CCD. This implies that you have done some testing before and do know what the linearity of your CCD is. Now, it is also important to understand that flats themselves need to have darks subtracted from them. Typically, one approach is to take dark exposures at the same time as the flats. However, some software, such as what we'll be seeing later, can take care of scaling the dark files that were obtained for the science images and use them for the flat darks. So in some cases, it's not necessary to take separate darks for the flats themselves. And as we suggested, taking an odd number of these calibration files would allow also it being an odd number so that a median combined could be used. And we strongly emphasize, as sort of tedious as it might be, to take calibration files for each observing session and to just get into the practice of doing that. Now let's take a look at the importance of flat fielding. Let's say that we start off with a star in this particular position. What you see here, by the way, is a sort of typical flat field, and you see various dust motes that are inevitable on the flat field. Let's say a star is in this position prior to a meridian flip. After the meridian flip, the star will cross over the diagonal and appear on this position of the CCD detector. Well, notice what happens here. If that star lands on a dust mote, all of a sudden the brightness of that star is going to be arbitrarily changed. And this is the reason for making sure that flats are done in correctly and in a uniform way. A master flat is created so that any of these aberrations due to dust motes are taken care of before the final processing takes place. So what we then suggest is that as far as testing a master flat is to first create a master flat from the flat images as you normally would do, apply the master flat to one of the raw flat images and see if you can detect any dust motes. And if so, that means that the master flat needs to be redone. So theoretically, the master flat applied to one of the flat images should eliminate any signs of dust motes. So now in the last phase, the post-processing and modeling phase, what we're going to be seeing in the next module is using a piece of freeware software called AstroImageJ to conduct this final phase where the after calibration is done, that the differential photometry takes place and the transit modeling occurs. AstroImageJ also does allow for calibration of the images. We'll see how that works. And also, AstroImageJ can update the FITS headers of the calibrated files with two important parameters that are needed for the transit modeling. The air mass, if that's not already included in the FITS header by the image capture software, and the BJD TDB times. You recall in previous modules why it's important to standardize on BJD time. And again, AstroImageJ will conduct the differential photometry on the calibrated file. Once this differential photometry is done, then AstroImageJ will be able to do a model fit. There are some prior parameters that will be entered into AstroImageJ, and these can be obtained from some of the online resources that we discussed earlier. Also, as we mentioned, the worksheet is a good way to record what these prior parameters are. Among the prior parameters are, first of all, the orbital period of the exoplanet as it transits its host star, the predicted ingress and egress times, the limb darkening coefficients, and optionally the radius of the host star. Now, the radius of the host star is used simply to be able to compute what the radius of the exoplanet is. It's not actually an input into the model itself, but it's used to conveniently display and compute the radius of the exoplanet. In addition, we will be seeing how certain D-trend parameters can be input into AstroImage-J. These D-trend parameters are used to compensate for such things as changes in air mass. We'll then be able to see through AstroImage-J how we can select and plot different light curves, for example, of the comparison stars. And this is necessary in order to be able to visually see if in fact there is any variability in the comparison stars. And finally, we'll see how we can deselect some of the comparison stars whose flux is variable in order to take them out of the model fit, or if in fact we see if there's a lot of scatter in particular comparison stars. So with this discussion of the various phases, we'll now be able to cover an actual observation and actually walk through AstroImage-J to see how AstroImage-J is used to do everything from the calibration of our science images all the way through to optimizing the model fit.